So folks, now that we've given both an intuition for limits of multivariate functions and we've looked at the definition, let's do some calculations of limits. At this point, we haven't justified any of the steps that we're about to take, but some of the justification is similar to what we do in Calc 1. So I'm just going to go ahead and do so. So we're going to take the steps to prove these in class, but let's go ahead and just evaluate some limits. Here I've got the limit of a function of three variables. By the way, we didn't actually specify this, but you would think of this as being a function w, which is equal to f of x, y, z. So it has three input values. And so as our arbitrary x, y, z values are approaching the point in 3 space, 3, 2, -1, so domain values, which are these ordered in tuples, are approaching this particular triplet, what does the function, what does the output, what does w appear to be approaching? And we're going to justify this in class, but the trick is that this function right here is continuous at the point that we're trying to evaluate the limit. So we're just going to use direct substitution, meaning evaluating this limit is no different or produces no different output than simply evaluating the function at that point. So we would say that the limit, and do practice writing this out, folks, so it doesn't feel intimidating, as the ordered triplet from the domain approaches the ordered triplet 3, 2, -1 for our function, that's just equal to f of 3, 2, -1, which is equal to 3 times 2 quantity squared times -1 cubed, which would be -12. And in this case, similar to some problems you saw in Calc 1, evaluating the limit was no different than simply evaluating the function at that point. We haven't proven why that's the case, and certainly most problems we encounter in this class will not be so easy. So here we have another limit of several variables that we want to evaluate. So in this case, our function would be a function of two variables, and it's the function x squared minus y squared all over x plus y, and that gives us, some z value in the in that third dimension. And in this case, and again, we haven't proven this, we're going to do a trick that we did in Calc 1. The trick is to find a function that agrees with ours everywhere except the limit point. Okay? So if I can find a function that matches this function everywhere except for possibly at the ordered pair 5, -5, then I can find the limit of that simpler function instead. Here we go. The limit as x, y approaches 5, -5 of x squared minus y squared all over x plus y. Well, I could give a comparable function to this. Notice that this function right here, the function x minus y, agrees with this function here everywhere except for at the point 5, -5. How did I come up with that? It's simply that trick that you did in Calc 1, where we said, hey, we could rewrite this as the function x plus y times x minus y all over x plus y. Now, in general, you can't cancel out expressions involving variables. But notice that at least for values around the ordered pair 5, -5, these two functions output the same thing. And so that's what I replaced. I replaced it with a function that agreed with ours everywhere except for at that exclusion point, or possibly other points, but at least far away from them. So what do I mean by that? Well, notice if I were to plug the ordered pair, say, 0, 1 into this function, that would give me, into this function here would give me 0 squared minus 1 squared all over 0 plus 1, which just gives me the number -1. And if I were to plug 0, 1 into this function, that would give me 0 minus 1, which also gives me -1. That's what I mean by this function right here, just this piece right here, agrees with this function everywhere except around the limit value, except for possibly at that limit value. But now we can just simply evaluate this one through direct substitution. which is a principle we haven't applied to multivariate functions, but it works in practicality similarly to the way it worked in multivariate or in functions of one variable. So this is just going to be 5 minus -5, and we get a limit of 10. Okay. So we're continuing on, folks. Here we've got the limit of this function here, and this is a brand new trick. This is going to be something you haven't seen for limits before. And we're asked to evaluate the limit of this function. Notice certainly that 0, 0, the origin, is excluded from the domain of this function. But we ask the question, how does this function behave near the origin? Does it behave in a predictable manner? And in which case we could say that the limit exists. So let's apply a substitution to this. We're going to do a substitution to this problem to make the function a limit of just one variable, and then we'll use calculus 1 on this. And this is a really clever technique. It doesn't always apply, certainly, but in this case, what I'm going to do is I'm going to let r squared equal x squared plus y squared. Then as x comma y is approaching the ordered pair 0, 0, that means that r is approaching the value 0. So what I can do now is I can rewrite this as the limit. So let's start off, we have the limit as the points that we're choosing are approaching the origin. But then we're doing this substitution, so we have that's the same as the limit as r is approaching 0. That's what we found here, right? We replaced the limiting point with the limiting value of the sine of r squared all over r squared. And if we were to take the, well, now this is a problem that is a one variable function. And so we've got all of our tools of Calc 1, and what should we use here? Well, hopefully you recall the Hopital's rule that was taught in Calc 1, which is a slick way of evaluating this limit, assuming we've already got the derivative of sine. So let's go ahead and apply Hopital's rules to this, which says that's the same as the limit as r approaches 0 of the derivative of the numerator over the derivative of the denominator. And notice that since we've got a function of one variable, we know what it means to take that derivative. So the derivative of the numerator would be 2r cosine of r squared all over the derivative of the denominator, which is 2r, and we can go ahead and cancel those two values. And so that gives us the limit as r is approaching 0 of just the cosine of r squared. This function can be evaluated by direct substitution, and we just get the cosine of 0, which is 1, and that's how that limit evaluates. By the way, folks, some of you might be wondering, I didn't have to actually use r squared. I could have just used r for this substitution, and it would still work. The reason why I picked r squared is you will see several other problems where r squared is the appropriate substitution to use. Folks, we did a very long introduction to the intuition of what we mean by a limit of a multivariate function. And we see that behind the scenes is this epsilon delta proof, which is exceptionally complicated and takes a while to understand. That epsilon delta proof can be used to prove a bunch of properties and other rules, which makes evaluating some of these limits straightforward. I want to caution you, though, with the example that we opened up with, our first multivariate limits that we looked at, where none of the limit rules that we've just looked at would be enough to be able to analyze the difference between these two limits problems here, where one, the limit didn't exist, and another, the limit was 0. So none of the techniques that I've discussed will help us with these two problems, and these are what we're going to be studying in class. And this is the key difference between the types of problems that you experience in Calc 1 and the limits of these multivariate functions. That finishes up our pre-work, folks. Go ahead and work the My Math Labs for these pre-works. Thank you very much.